All right. So I'm hoping that by recording this, I'll be able to get it up to uh, like YouTube, or maybe there's some place that I can like upload it so it's easily navigable. Um, Hopefully, if it's not up on YouTube, I can make it accessible somehow, either on the tutoring link or somewhere otherwise, but we'll see how that all goes. To fix my hair. I'm gonna try to do a little bit of processing on it as well, so that way all the like filler and time like that is taken out. But we'll see how it is. Yesterday I did this lesson and we finished up about 15 minutes early. So if we do, that's great. If not, it doesn't matter to me one way or another. Cool. All right. So what I wanted to go through today was acid and base stuff. So how can I like there should be a way to maybe if I do that. No. I don't know. We're just gonna have to go with it. All right. Can you guys see the drawing screen yet, by any chance?
No, not yet.
Okay. Let's try. Let's try. There. Now can you see it?
Yeah.
Sweet. All right. Let me fiddle with the settings. Perfect. And are you guys able to see me right with the pen? Sweet. All right. So with that in mind, we are all underway to talk about probably one of the uh, most integral part of chemistry. It shows up everywhere is acid and base chemistry. Now, a big portion of this is going to be to teach you guys, you know, obviously what you have to know for orgo, but also to kind of demystify a lot of kind of the big words that came out of Gen Chem and how they apply to orgo. Because not everything that you learned in Gen Chem is exactly what we're going to be pulling over, but we're going to be building upon it. Um, and so what I want to do is I really want to break down some of the bigger key concepts that people always get confused and they have a hard time with. So in acids and bases, in this great big old field, we have a few different definitions of acids and bases that we can go with, but in organic chemistry, the primary definition that we're going to be concerning ourselves with is the Bronsted-Lowry acid and base definitions. All right. So Bronsted and Lowry are two guys, and they came up with this amazing way of looking at acids that really creates a more rounded way. That's not to say that the other definitions are not important. It's just that in organic chemistry, their definition reigns supreme. So if you guys remember from Gen Chem, we kind of have this setup going on using all of our very nice colors. Guys kind of sort of remember this from last year? Yeah. Also, if I go too fast, tell me. I'm happy to slow down. I constantly repeat myself as well. So, but if something doesn't make sense, let me know. So, if you guys remember from last year, we set up this kind of weird equilibrium going on. And essentially, what we're talking about is that we have two things happening almost at the same time. And before we dive in, we really have to talk about, well, what are the definitions that we're saying? And this is what I will drill into your head over and over and over again, is that acids donate protons, or that they donate hydrogens. So acids donate. One more time. Acids donate. So what do acids do? They donate hydrogens or protons. So I don't ever, ever, ever want to see you in one of your exams put that acids accept protons, because they will never do that. That is not what an acid does according to Bronsted and Lowry. By contrast, bases accept protons, or they receive protons and hydrogens, all right? So these are the two primary definitions that we're going with, all right? And notice how general they are. They donate hydrogens, or they accept hydrogens, all right? So this is a pretty general way that we can describe molecules. And so if we go back up to our kind of symbolism up here, what we see is that this molecule with its lone pair of electrons can come and squiggle its way over, whoop, wrote it the wrong way, can squiggle its way over and grab this hydrogen. Notice that I'm drawing the arrow from the electrons to the hydrogen, okay? Because you have to physically reach out and grab something. We can't just say the hydrogen, swims over to this B species. It has to be grabbed by something, and it's grabbed by a lone pair of electrons. And so the question becomes, is this compound here, HA, is this donating a hydrogen to B? Is it giving up a hydrogen? Yeah, totally. And because it is donating, it is an acid. No ifs, ands, or buts. And when we look at the resultant, we can see that the A species has donated over the hydrogen. It's gotten rid of it. It's gone. Doesn't want it anymore. It's all good. And by contrast, this B species has accepted the proton that it was given, and so we can call that the base. Pretty familiar from Gen Chem, should make sense, not super overly complicated, pretty much the same information. What's special about Bronsted-Lowry that kind of separates it from the other definitions is that it sets up this other half of the equation, where there's no reason why this leftover A species can't reach out and grab the hydrogen. And so what this is telling us is that this A negative, this A right here, is acting as a base. So this is the conjugate base of the original acid. And because HB is donating to the A, it's the conjugate acid of the original base species. So you're always going to have this double kind of pairing going on. Acid and base, conjugate acid. And so we can always, always, always set up this pairing going on. Does this make sense? Sweet. From here, well, how did we get these charges? Well, let's take a look. Originally, the charge on this acid was neutral, and it's losing the positive charge in the hydrogen, and so now it's negative, which is how we get that. Likewise, this base was originally neutral, and it's gaining this hydrogen, and now it has a positive charge, which is how it gets that. Does this make sense? Sweet. And so this is how we set up this Bronsted-Lowry equilibrium reaction going on. Acid base, conjugate acid. And once again, do not forget, acids donate, bases accept. Really is like fundamental. And if I find out that you say otherwise, I'll kick you in the shin or something like that. We'll figure it out. Cool. So from here, what we can talk about is one of the things that you learned in Gen Chem that probably is one of the things that people know they're like still confused about, which is the idea of Ka, or more specifically pKa. And so this is the question that people always come up and they always point at this and they're like, well, what the fuck is Ka? That's the question they always ask. And that's the chemical way of saying it. What the fuck? So what I'm going to tell you is that Ka is the acidity constant. Constant with a K because it's German. So what is this saying, the acidity constant? Well, it's telling us it's the dissociation constant as well. I think there's two S's in there. So it's the dissociation constant. So basically what this is saying, I need to move that up there, is that when HA donates, it dissociates into H plus and A minus. And so it's measuring how likely this dissociation between the proton and the A molecule is. And so if it dissociates very strongly, we can say that it's a very strong acid, because if it dissociates, it donates. If you dissociate, you donate. So this brings us to the question, well, what is Ka really? And Ka is just a numerical way of determining the strength of an acid. That's all it is. Ka is just a way of putting a number to how strong something is. That's all it is. It measures the dissociation, and if you dissociate, then you are an acid, but it's just a number. That's all it is. So what's someone's favorite acid in the world? Someone give me an acid. How do we feel about hydrochloric acid? Is that one good? And when we look at hydrochloric acid, the Ka of this is 10,000. So it has a dissociation strength, we could say, of 10,000. Not those exact words, but something that we could say that. And something very common that we use in the chem lab is acetic acid, and that has a Ka of 10 to the negative 7th, or in other words, 0.000001. And so by looking at this, we can clearly see that hydrochloric acid, HCl, is much, much, much stronger than acetic acid, right? In fact, HCl is 10 quadrillion times stronger. But here's the issue. If I work with these things in the lab and I want to measure the acidity of my beaker or something like that, how can I make a graph that goes from 10,000 to 1 millionth? You know, how can I make that graph? It's almost impossible, right? You can't make a scale that fits nicely on a piece of paper that goes from 10,000 to 1 millionth. It won't happen. Not to mention, too, that, I mean, I don't know, I haven't seen ever 10,000 things and been like, oh yeah, that's 10,000. Or even looked at 1 millionth of a thing and been like, oh yeah, that's a millionth, right? These are numbers that don't even quantify in my head. So what we're going to do is we're going to use a function, and the function that we're going to use is P. And what P is equal to is the negative log. So what we're going to do is we're going to take the pKa of hydrochloric acid. And what we find is that the negative log of 10,000 is equal to -5. And then we're going to take the pKa of acetic acid, and what we find is that it's equal to 7. Oh, okay. I can rationalize in my head what -5 kind of looks like and what 7 looks like, right? I can also put -5 and 7 on a graph, right? That scale is so much more manageable than 10,000 and 1 million. That is all pKa is. Its pKa is just a fixed scale. It's a fixed scale Ka. That's all it does. Is it still measuring the strength of an acid? Totally. But it just means that we can put it on a graph better. That's all it's doing. Does this make sense? And by doing this, we can't change this fact that hydrochloric acid is 10 quadrillion times stronger. All right, we can't just fiddle with the numbers and invent something new. So what's important to know is that every step in pKa is times 10 the strength. So every time that, if we're talking about a strength of 2 compared to a strength of 3, this is 10 times stronger, not, 1 time stronger, okay? So likewise, if we're talking about a strength going from 2 to 4, this is 100 times stronger. And this is the thing that people forget, is that we're using a log scale here. And so a log scale makes every step worth 10. Does this make sense? Sweet. Sweet, sweet, sweet. This is probably the thing that people get most confused about in organic chemistry, especially for the first exam, because they don't really get what pKa is, and this is all it is. All right? So all you have to know about pKa is it's just a way of measuring the strength of an acid. Big important note to know is that the smaller, which is just, or you could say, or more negative, a pKa, the stronger the acid. And so just like how knowing that acids donate and bases accept, this is the other sentence that you are going to have to just really have to memorize, that small pKa, strong acid, big pKa, weak acid. Small pKa, strong acid, big pKa, so weak acid. All right? So with that in mind, we can go on and we can take a look at, let me give you guys a good Pka table. So in the chat, I'm going to put in a really good Pka table that I recommend everybody use. It's on the Mastering Organic Chem website. It just looks really clean, and it shows you the name, the acid, the conjugate base, and the pKa. So it's very straightforward. That table will become your best friend. So bookmark it, tattoo it onto your forearm, whatever you have to do. Cool. Good with this so far? Yes, no, not really. Good? Great. Sweet. All right. So next we're going to go on and we're going to start talking about, well, how do we actually do the acid-base problems that you're expected to do on your exam? And what I'm going to tell you is that in an acid-base reaction, you're going to be asked to do three things. The first thing is you're going to want to determine who is the acid, the base, the conjugate acid, and the conjugate base. So that's what we want to find. Then you need to assign the correct pKa values. And then finally, we're going to determine the equilibrium. And so by doing these three things, you're going to get 100% on your acid-base questions. All right. So the way these are going to look on your exam is that you're going to be given two structures. So let's say, I don't know, this is your first one. And you're going to react that with, I don't know, this guy. And then you're going to see this double arrow, and you're going to see blank spot plus blank spot. And then below it, you're going to see pKa equals 4, pKa equals 35. This is all the information that you're going to be given. I'll give you a couple seconds just to copy it all down. There's a bird who keeps flying into the window. I don't really know what to do. All right. So just to make these things easy, because I believe that, we could talk about the specific chemical name that's going on, but I'm just going to label this structure Dave. And I don't know, this one looks like a Nancy. So we're talking about Dave and Nancy here, all right? And Dave and Nancy are going to react in an acid-base reaction, all right? So the first step is to assign who is the acid and who's the base, all right? Well, the big thing that we have to know is we have to determine who has a proton that can be donated. And so if we look at this functional group here, which this is a carboxylic acid, in case if you guys are studying those, which you should be. And what I can tell you is that this hydrogen here has a partially positive charge. Versus if we look at this Nancy structure over here, what do you notice about the charge on the nitrogen? It's negative, right? So do we think that this nitrogen is going to want to come over and take this hydrogen? Totally, right? Negative is attracted to this positive hydrogen. And so we can say that this is how the reaction is going to go. Well, how do I know that? How do I know that this oxygen doesn't want to grab that nitrogen, or this hydrogen on Nancy, right? Well, how can I be sure of that? Well, the big thing is that if we go back to our original Bronsted-Lowry setup, if we look at what's going on, notice how this base has a negative charge. So bases in general will have a negative or neutral charge, whereas acids will have a positive or neutral charge. So if we go back to our problem over here, we know that acids, I'll just rewrite what I just said, acids can be positive or neutral, whereas bases are negative or neutral. So both of them could be neutral. So as of right now, Dave could be an acid or a base because he's neutral. So we look at the other structure and we see, oh, okay, this is negative, and negative means a base. And so I can say definitively that Nancy is a base. Does this make sense? This sort of way of thinking about it. Okay? So the big thing about identifying acid or base is just finding out where's the hydrogen that's going to get donated and where's it going to go to. So who's donating and who's receiving? And because Nancy is the base, because we can say that Nancy is the base, we can say that Dave is the acid. All right? If one thing is the base, the other thing must be the acid. Does this make sense? Sweet. What I can do is I can label the other side now, and I can say, okay, well, if Dave right now is the acid, then his conjugate must be the conjugate base. And I can say the same thing about Nancy. Nancy must be the conjugate acid. And I don't know, what we'll call this Dave 2.0, and we'll call this Nancy 2.0. All right. So we've already completed the first step, finding out who's the acid, who's the base, who's the conjugate acid, and who's the conjugate base. 3 points. Perfect. Now we have to make sure that we're assigning the pKa values correctly. Remember, what does the A stand for in pKa? It stands for acid, right? So we can only describe structures that are acids with pKa. So can I describe Nancy, who is a base, with a pKa? No. Nancy is not a base, so I cannot describe Nancy with a pKa value. However, I can describe the conjugate acid with the pKa value. And so this is what you have to do on your exam, is that you have to identify which pKa value are we going to cross out and move to the other side. Because you cannot describe a base with a pKa. You cannot describe a base with an acid constant because this is not an acid, it's a base. However, I can describe its conjugate acid with the pKa described. Does this make sense?
I have a question.
Sure.
So when looking at the conjugate acid and base, knowing that we either lost or gained a hydrogen atom, how do we know the pKa is still the same number?
Very good question. So this is going to come apart from there are certain pKa values you have to memorize for your exam. So if we look at what the structure is going to be, so we know that Nancy is going to pick up this other hydrogen, and so we know it's going to turn into an NH2 group. This NH2 group is an amine functional group, and amine functional groups have a pKa of 35. So basically, to answer your question, is that you know that this is the pKa value is correct because the functional group that you create is going to be the same. Does that make sense?
Yeah, thank you.
Mm-hmm. There are times where you create a totally new functional group that's not labeled with a pKa, or even in fact, maybe he won't even give it to you. But those are situations that as you practice more, you'll be able to like figure out and everything like that. Not today, but the next time we meet, or depending on how the scheduling works out, I can give you guys like a way of doing it. But sweet. So same thing, we can fill in what happens with Dave 2.0. Dave 2.0, we know that everything is going to be the same, except now that this oxygen here is going to be deprotonated. and he's going to have a nice negative charge. And once again, we can go back to our definitions of acids and bases, is that acids are positive or neutral. Well, this conjugate acid is neutral, so that's totally fine. And this base is negative or neutral, and look, there's our negative charge. Does this make sense? Sweet. The last part is we have to determine the equilibrium, which way the equilibrium lies. I guess I should have put that in, lies. And basically what we're trying to say is which arrow is Mother Nature going to favor? Are we going to favor creating more of the products or more of the reactants? And what you have to do in your exam is circle one of these arrows. And so there's two ways that we can do this. The first way is thinking about it logically. And the second way is thinking about it mathematically. So let me put it this way. For the logical way, if you had two kids in a room with you, and one of them was kind of like playing nicely by themselves in the corner, not bothering anyone, just kind of hanging out, doing their thing. And then you had a kid that was screaming and like kicking you in the shin and being like really, really all over the place. Which one are you going to throw out the window? You're going to get rid of the screaming kid, right? They're annoying, they're reactive. So the Mother Nature, MN, will always create, or I should say, will always favor the weaker acid. And it has to do with how reactive it is, how high in energy it is. Mother Nature will always try to get rid of highly reactive molecules. So it will favor having weak things in solution more than strong things in solution. And the reason for that is because strong things are going to rip things apart and kill babies. So we want to make sure that we're creating weaker acids so they're more stable, lower in energy. Does that make sense? Sweet. The mathematical way is looking at a different constant, and it's called the equilibrium constant. And basically what this is mathematically saying is that the equilibrium constant is equal to 10 to the product pKa minus the reactant pKa. And so if we wanted to do it for this problem, we could say that this is 10 to the 35 minus 4, which is equal to 10 to the 31. And so what we can say is that when KEQ is greater than 1, we're going to choose the product side. And when KEQ is less than 1, we're going to choose the reactant side. And so 10 to the 31 is, 1 with 31 zeros after it. So that's, more greater than the number of particles of sand on a beach. So we're going to be, that number is greater than 1. So we're going to be choosing the arrow that points to the product side, which also has the weaker acid that Mother Nature is favoring. So we're going to circle the top arrow. And so this is how you get maximum points on your exam by doing all this work. It gets basically secondhand nature the more you work with it and the more that you do it. So I highly, highly, highly recommend doing practice because it'll be like, oh yeah, boom, makes sense, perfect, done, and everything like that. Let's do another practice, shall we? Oh, I don't know. Someone give me like a flavor of something, like something that tastes good. What do we think?
Mango.
Mango? Ooh, uh, don't know that one. Um,
Strawberry.
Strawberry is a good one as well. Let's take a look. I'm gonna take a slightly modified version of the mango flavor. So maybe it won't taste exactly the same, but you know what? Don't blame me if you try to make this in the lab and it tastes badly. And then someone else said strawberry. Oh, wow. That's a weird structure. Come on. There we go. By the way, don't be lazy and do this. Don't do that. You don't know what this means. All right? You have to put the 3 lines. Don't have my permission to do the circle yet. If you're in Shia, you'll learn what it is. If you're in Poulos, you won't. But otherwise, I don't want to see it. All right. So here's our 3 things. I didn't really leave myself enough room, so I'm just going to write it kind of like that. And so we have like a mango derivative and a strawberry derivative, and we're going to react these 2 things together. And we're going to see what happens. So the pKa of this, I'm going to tell you, is 2.7, and the pKa of this guy up here is going to be, oh, I don't even know what this one is off the top of my head. Little pKa 16. I think it's indole. Can't remember. Yeah, it is. Cool. So we have these 2 structures. Here's our mango structure. Here's our strawberry structure. And so first step first is we need to determine who's the acid and who's the base. Well, easiest way to do it is check, are there any charges, right? So I check this and, oh, well, this is neutral, so that could be anything. And oh, this is neutral as well, so that could be anything. Okay. Well, we have a bit of an issue because neither one of this is telling us which one is the acid in its current form. So we can take a look at the pKa values. And what we have to do is we have to do a little bit of kind of mental guess and check going on. And we said, let's assume that both of these structures could act as an acid in their current capacity. Who's the stronger acid?
Mango.
The mango one, right? So with that in mind, if mango is the acid, then that means that this pKa would get moved over, right? This nitrogen has the capacity, it has 2 lone pairs. Sorry, it has 1 lone pair, two electrons, to be able to pick up this hydrogen. And so the rule of thumb that I'm going to give you is that nitrogen is always a base unless it's positive. And it's positive when it makes 4 bonds. And the reason why this rule of thumb is in place is because nitrogen is really, really, really hungry base. It loves hydrogens, especially because it has these nice lone pairs going on. Okay, so this lone pair is really, really, really good at picking up extra hydrogens. All right, so with this in mind, what we're going to say is strawberry acting as an acid or a base right now? It's acting as a base, right? This is a base. And we determine that because this pK is lower, that this is the acid. Just by saying, okay, here we have a nitrogen with a lone pair. Here we have an oxygen that has this nice hydrogen that it can donate. And so this nitrogen is going to come over and it's going to grab that hydrogen. Does this make sense? And so this is the crux of what acid-base chemistry is really the hardest bit, is determining, okay, well, who's the acid and who's the base? So from here, we can say that, you know, this structure is the conjugate base. This is the conjugate acid. We can fill in all that great information. We can even, at this point, copy our structures and just show what they're going to look like. So we know for mango is going to be donating this, this hydrogen. And so if we wanted to, we could check it with the math as well, that it's currently neutral. It's losing a positive charge, so it's going to have a -1 charge. And then for strawberry, I'm going to have to move this. Strawberry has it's going to gain that second hydrogen right on the nitrogen. And what we could say is that it was originally neutral. It gained that positive charge, and now it has a +1 charge. With me so far? Perfect. From here, now we just need to, we've determined who the acid, the base, the conjugate acid, and the conjugate base is. Now we have to assign the correct pKa value. Is this pKa in the correct place? Is this pKa describing an acid? Yes, it is. So this one is fine. Is this pKa in the right place? No, it's trying to describe a base, so we move it over. Again, if it's hard because you guys don't necessarily know this functional group, I'll give you a list of pKas that you should be familiar with at the end of the class, so that way you can start learning them and like put it into a Quizlet, super simple. But this is one of those pKas that you'll be able to pick up and be like, oh, okay, that makes sense. And that'll be one of those things. Cool. So from here, now we just need to choose which way the equilibrium lies. And so we can think about it logically, and we can say that Mother Nature will always, always, always try to create the weakest acid. So we're going to be choosing towards the products. Likewise, we could do the math out, and we could say that it's 16.2 minus 2.7, which is 10 to the like 13.5, something like that. And this is greater than 1, so we can say that it favors the product side. Does this make sense? kind of straightforward, right? Let me show you guys what it looks like on the exam, so that way you can see what it's going to be like. So if you go to Google and you type into Google, you'll see my tinyurl.com/Gabe Tutoring. So if you type in this link, it will take you directly to the Google Drive. You guys are in second year, so you want to go into second year stuff. You're at MCPHS Orgo, so you want to go into there. First semester, and here is a whole bunch of guides and tools and references that you can see. Some of this stuff I haven't checked in a while, so I'm going to have to go back over it. But let's say, for instance, oh, you wanted to see how I wrote something out again? Oh, look, here's all the same notes, and they're exactly the way that I say them, and everything like that. So if you ever need to find something that I've done, usually it'll be in there. If not, message me, and I can send you the lesson plan. If you look in right here, here is the blank exam for Poulos for 1 through 3. I know I have Shia exams somewhere. I will have to put them up. I think I have other Poulos ones as well. They're just probably somewhere. But so scrolling down, what we see is oh, here's the acid-base problems that you guys will have to do in the exam. And Chia's exam looks extremely similar, so it's going to be the same. And so you're going to have 2 structures, and you're going to see that, oh, here's the 2 blank spaces, and you have to choose the arrow. Also, he puts it so it says for the conjugate acid. So this tells you, okay, this pK is not describing this structure, it's describing the other one.
Hey, Gabe.
Mm-hmm.
Do you know how they'll be online? Because right now we're kind of limited to like multiple choice exams and stuff, and that's all we've seen. So do you know how it's going to vary?
Basically, the way that it was in the spring is that you'll have questions will be divided kind of in like 2 parts. So the first part will be, he'll show you multiple different instances of the product, and he'll be like, choose the correct product pair. And then it'll be like, which way does the arrow lie towards the products, towards the reactants, stuff like that. Think it'll look something similar to something like this. So like, examine the proton transfer acid-base reaction and determine the KEQ. So it's like, this is how you would go about it, or something similar to this. Does that make sense?
Yeah, thank you.
Yep. Cool. So I just want to show you, I want to go through this problem with you, just so that way we can practice one more. I'm going to swap over to back to the whatever it's called, the smooth draw. This summer I tutored, and my like hexagons and everything like that were brilliant. They were perfect. And then I lost it all. All right. And the pK that he lists is 1.10. And the pK he lists over here is 10.6. And he tells you that this is for the conjugate acid. And so this is everything that you're given. I'll give you guys a couple seconds to write everything down. Oh, what's some good names that we can give this? 2 nitrogens. This needs like an N name. So let's say it's, I don't know, call this Nora. And with it, this will be Steven. Because I feel like me telling you guys, oh, pyrimidine hydrochloride doesn't really help you with figuring out which structure I'm talking about.
What is like the /CL and the /K mean?
Very good question. So these over here are spectator ions. They're also the same way that you could say it is saying countercharges or counter ions. And basically what it's saying is that you can't just have negative things in solution. They have to be associated with something. And so the positive charge on the nitrogen is associated with the chlorine, and the negative charge on the sulfur is associated with the potassium. So just like how we could write NaCl kind of like this, that's all it is. It's just showing you the charges. But these will play an important role in getting your question right on your exam. And I will show you that. Cool. So first steps first is identify the acid in the base. So is Nora or Steven going to be the acid? What do we think? I think probably Nora is going to be the acid. And there are a few different reasons why I can figure that out. One, we have a positive species. Generally, acids are positive or negative or neutral. So a positive really clues you in, oh, this is probably the acid. Likewise, this right here is telling me it's the conjugate, the pKa for the conjugate acid. So this pKa is not describing this structure. This pKa is describing the conjugate acid, which is down here. And so what I can kind of do almost immediately is just bring this right down and be like, oh, here's where the pKa should exist. Does this make sense, this rationalization that we're going on? So if Nora is the acid, that means Steven must be the base. Likewise, the conjugate base of Nora is right here, and the conjugate acid of Steven is right there. So Steven 2.0, Nora 2.0. So on your exam, you can rely on the fact that it tells you, oh, the conjugate acid is across the arrow. So this clues you in that you can just move it immediately. But don't forget that sometimes they won't give you the pKa's. So that's on you for the ones that I will tell you to be familiar with, to make sure that you're memorizing and that you're familiar with, so that way you can figure it out even if they're not given to you. Cool. So from here, we are figuring out where the proton transfer is going to happen. And so we know that it's going to come from the negative sulfur. It's going to move its way over, and it's going to grab the hydrogen. And so what we can do is we can redraw our two structures. Oops. What's that? Boom. So we have our two structures that show the proton transfer that happened. And so the last part is now that we have to choose which way the arrow is lying. So are we going to be making more reactants or making more products? So we have to look for where the weaker acid exists. And the weaker acid is here. so we're going to be making more product. It's not always making more product. It just so happens that this is just how the problems have worked out. And we're all done, right? No, we cannot forget our nice countercharges up here. So this chlorine is going to associate with the positive species that's left over. Oh, well, this is neutral, and oh, this is neutral. So what happens to this negative chlorine? Does it just kind of explode and like Thanos snap its way out of existence? No, it associates with this potassium ion. And so what we write off to the side is K plus Cl minus. And we can put, you know, if we wanted, we could put this in brackets, or we can write it off to the side. So this is the thing that, you know, has he talked to you guys about the format of the exam? So if I remember correctly, actually, there is a written portion, and you have to upload a picture, I believe, or like a scan of your, I think it's like a take-home portion. So these problems might actually be in the written portion, and all the multiple choices given online. I can't remember exactly the way they did in the spring. I'll follow up with a someone who took Orgo in the spring, and I'll post a thing on my Snapchat about what the format will look like. Unless if, because you guys do your stuff through Exemplify, right? Or ExamSoft or whatever it's called. Oh, you do you do it through Blackboard? Well, however they do it, I'll let you guys know how they did it last year, and then and maybe that'll give you a clue in. He should be telling you probably this week about how it'll happen. Cool. How do we feel about acids and bases? Good, good, not so good, bad, don't understand it at all.
I have a question.
Sure.
So in the first like acid, there's an N and then it's plus. So why does it become neutral in the conjugate base?
Good question. So if we take a look at how the charges work out, currently it's +1. It's losing that positive charge from the hydrogen, which makes it neutral. And I try to stay away from the arrows because it's kind of a little bit too early in the course and people tend to get confused about it. But what ends up happening is that, don't forget that there's 2 electrons that are shared between the nitrogen and the hydrogen. And so essentially what's happening is that both of these electrons are being sent to the nitrogen, which is what ends up making it neutral. A little bit more involved than what we have to go into right now, but in case of anybody is wondering. Cool. Definitely recommend going through the blank exam and doing there's 6 problems in there, and then there's some more that are in the multiple choice, and just going through them and understanding them. Super, super, super important to really kind of get that under your head. What I'm going to do right now is I'm going to give you the list of functional groups that you should know the pKa's of, kind of off the top of your head, or at least be familiar with, I guess is the better way of saying it. These are the ones that show up most commonly on these exams, and so if you're able to just kind of pull it out of your head, you're much better off. Although I know that you guys have probably been memorizing a ton of stuff so far, and it's just more stuff to memorize. But the pKa's you should know, and I'm not going to give them to you. You should go and look them up on the Pka table that I put in the chat. You should know HI, HBr, HCl, HF, hydronium ion, carboxylic acids, water, alcohols, phenol, amine, and protonated amine. Let me just make sure that that's in the, yeah. And if it gives you a range, just pick some number in the middle, some number that clicks with you. Cool.
What does the P one say? Yeah.
Phenol. So this is, phenol is a benzene ring with the OH stuck on the end. This is, no. And the acidic hydrogen is that one right there. Cool. Very nice. Good. Sound good? Sweet. So transitioning into the acidity trends now, and this part of the lesson plan is a little bit dense, purely because I'm just throwing tons and tons of information at you. I've tried to figure out ways of like making this a little bit less and dense and more fun, but honestly what it turns out to be is that actually I wonder if I really need to do the full bit. I think I can just do inductive. I don't. Yeah, I think I can do. Oh, sorry. There's two more. There's three more in here. Ha ha ha. Alkanes. Let me write this. Alkanes, alkenes, and alkynes. These are the last three. All right. What I'm going to tell you is, so for the acidity trends, there are 5 trends to know. What I've seen over the couple of years is that I've taught all 5 of the trends, but what I'm starting to see more is that only really one of them is really talked about. So what I want to show you is that in that same Google Drive link, if you go to this PowerPoint called Acid and Base Chemistry, and you go into this PowerPoint, I go through all the acidity trends and I talk about them. The main one that we are going to be talking about right now is the inductive effect, because this is the one that really ends up playing a bigger deal in terms of the test. All of these are important to know, but this is the one that people end up asking me about a little bit more. So what I would say is either go take a look at the PowerPoint for the other ones, because they're pretty straightforward. And if you have any questions or anything like that, let me know. This way we can at least do like another topic as well, like naming or talking about different things that you want to talk about for your exam. Cool. Let's just do that. I think that'll end up being a better use of our time. Sweet. So the inductive effect. The inductive effect is kind of a special process that happens in molecules. And essentially what we're trying to do is we're trying to increase the electronegativity, trying to increase the acidity of a molecule by adding electronegative atoms. Atoms / groups. All right. And as a quick refresher, electronegativity, don't want to do that in green. In a simple way of describing it is just, it's a measure of how hungry an atom is for electrons. So the higher the electronegativity, the more hungry for electrons they are. The more likely you are to pull them into your sphere of influence or your orbital and to create and to kind of hold on to them. So if you're highly electronegative, you want electrons more. And so what I'm going to tell you about acidity trends, so this is kind of the first bullet point. The second bullet point is that to increase acidity, we want to decrease the effective negative charge. To increase acidity, we want to decrease the effective negative charge on the conjugate base. And let's take a look at that. Let's take a look at why that's true. Here's our Bronsted-Lowry equilibrium once again. And if someone could just quickly remind me, what's the definition of an acid again? Does an acid donate? Oh, right, it does, because we're not ever going to forget that fact that an acid donates. So the question becomes, if you donate your electron or your hydrogen, so if you donate it, but then you immediately take it right back, boom, you give it away and then you take it right back because you're, I don't know, maybe it was a really good present or something like that. You don't want to give it up. If you immediately take the proton back, are you an acid? What do we think? If you immediately take the proton back, did you really donate it? Yes, you did donate. Remember, the definition of an acid is, do you donate or not? It doesn't talk about, oh, if you take it back or not. If you donate, you're an acid. However, if your conjugate base is strong enough to rip it right back from where it was, you are a bad acid. You are a weak acid. So if an acid donates, and the conjugate base steals the hydrogen back, that is a weak acid. Because remember, acids donate, but if you don't really end up donating, then you're really bad at your job and you're a weak acid. Okay? So what this brings up is the idea of measuring acid strength by the stability of the base. Highly negative bases are strong bases. So if you have a big negative charge on your conjugate base, you're going to take that hydrogen right back, and you're going to decrease the acidity of the molecule. Okay? So the strongest acids in the world are the weakest conjugate bases and the reason for this is because the conjugate base is unreactive. And the reason for this is because weak conjugate bases have small negative charges. Does this make sense? Any questions whatsoever? Any repetition anywhere? I don't mind. No? Okay. I just remembered that I have this star pen that I can like put everywhere. There's also, I don't understand the software. There's also grass. In case if you just want to add grass, like, oh, strongest acids hiding in the grass like a lion. Cool. So this is all well and good, but we started off talking about inductive effect, right? And we originally said that we're trying to increase acidity by adding electronegative atoms, right? So what does this whole spiel that I talked about small negative charges have to do with this idea? Well, let's take a look. Let's say that you have, this molecule, which is ethanol, which we should all be familiar with because we're all nasty college kids who get drunk all the time. And let's say, for instance, that you're donating off this hydrogen to somewhere. We don't really care. And what you're left with is this leftover group. All right, so this is our first instance of a molecule. By contrast, let's say that we have this molecule, but now I'm sticking a fluorine onto it. Now, remember that the electronegativity of fluorine is 4.0, and the electronegativity of oxygen is 3.4. So who's more hungry for electrons? Oh, it's fluorine. So what this means is that when we donate off this hydrogen, what ends up happening is that all these electrons that were on this oxygen, all these electrons that are over here, are slowly being sucked away, slurped up, eaten by this fluorine. They're being sucked right out of the oxygen. And so what happens is that we effectively are making this charge smaller. So now it's a little tiny baby negative charge. All right? So remember how I said that bad acids are weak acids are ones that reach out and grab that hydrogen that got away, right? So which do we think is the weaker acid? sorry, which do we think is the weaker base? The one with the big, strong negative charge, or the one with the tiny little baby negative charge? Which one's stronger? It's going to be the full charge, right? And so this is a weaker conjugate base, and weaker conjugate bases do not accept back a proton. Which means that they stay as the conjugate base and that they do not go back to being an acid. And this is what the inductive effect is that by adding electronegative atoms, we decrease the effective negative charge. By adding electronegative atoms, we decrease the effective negative charge. Does this make sense? Cool. And so what we can see is that the pKa of this acid over here is somewhere around, I don't know, maybe it's 17 ethanol, whereas the pKa for this guy is probably somewhere around 12. Maybe that's a little bit, maybe around 14. So what we've done is that we've made this acid stronger by adding a fluorine. All right? By making the conjugate base weaker, by making a weaker conjugate base, we have increased acidity. And we've increased it by 1,000-fold. All right, so it's a huge change. So what does this mean for your exam? Well, on your exam, you're going to be given a problem that says rank the following acids. And you're going to come across something like this. You're going to see CF3 CH2OH. And then you're going to see something like CH3 CH2OH. So this is the two compounds as they're written out. And so which one do we think is going to be stronger? A or B? It's going to be A, right? Because these fluorines are going to be slurping that negative charge away from the oxygen and increasing acidity. So on your exam, you're going to be given a compound that you know about. Here's an alcohol, and then you're going to be given a fluorinated group. And you need to know that the inductive effect says that the more electronegative atoms, the stronger the acid. The more electronegative atoms, the stronger the acid. Does this make sense? And so this is where these acidity trends are going to show up, is that the acidity trends are super easy if you just are able to recall those pKs of the ones that like list that I gave you. A lot of this kind of like theory work kind of is for nothing, but this idea of inductive effect is huge because you can't memorize every functional group and then all the fluorinated versions of the functional groups. It's too much work. So knowing that, you know, if the pK of this is 17, maybe this is somewhere around 14, or maybe I want to choose 13, or maybe I want to choose 15. It doesn't matter. All that it matters in your head is that it is below 17. And remember, smaller pKa, stronger acid. The other portion to know about this is that the inductive effect is made up of two portions. The first portion is the number of electronegative atoms. And the second portion is their proximity. And this should make sense, that if you have a compound that looks like this, versus a compound that looks like that, B is the stronger acid. Why? Because it's closer. Less distance for these negative charges to have to travel. And that should make sense. So if you have more electronegative atoms and they're closer, you're going to be dropping that pKa super low. Does this make sense? Sweet. I highly recommend going, and I'll post in the chat as well. Mastering Organic Chem has a really, really good lesson on the acidity trends. For this, I think I pulled a lot of information from them, or at least the way they phrase things. So you can definitely take a look at that. If not, go check out the PowerPoint. Honestly, it's pretty straightforward. The inductive effect is probably the one that's most challenging. But what I will tell you is that when you're going through and whenever you're working on any of the acidity trends, this fact about decreasing the effective negative charge on the conjugate base is true for all the acidity trends. So if you're ever like, oh, I don't really get this, think about how the negative charge is being reduced to a nice baby negative charge. Does this make sense? Sweet. Big stars. I can also make them smaller. I can make them like huge. What else is in here? Oh, there's another one as well, if I remember. Butterflies. Like what the, like why? Who knows? All right. This is the end of the acid-base material that I had prepared for today. Is there any questions about acid and base, or any questions about other topics that you can think about right now that you're like, oh, I didn't really get this in class, can you go over it? Or if someone wants to let me know what you guys are doing on Monday, then I can give you kind of like a pre-lecture to what's going on, whatever people prefer, or you can log off and go have dinner, whatever works for you.
I have a quick question, if you don't mind.
Sure.
So when you're looking at all these different effects that affect acidity, how do you know which one it is? So like we had an example one time, and it was just like there is like a sulfur, because you can use the electronegativity, but you can also use some of the other effects. So I was just wondering how to know when you're using which one.
Good question. So if you look in the Mastering Organic Chem or the PowerPoint, they're listed in order of priority. So it has to do with, oh, these are butterflies. It has to do with kind of what point differences are we talking about. So if we take a look at something like, like these 4 compounds. Something like, because this is kind of sort of like what it is, right? And then there might be like a carboxylic acid or something. It's easy to see that these first 4 compounds are really close and similar to each other, right? Where the only difference is, you know, oxygen versus nitrogen, or where fluorine might be, right? And so this is where I say going and knowing those pKa tables is really helpful, because this functional group is an alcohol, and this alcohol's pKa is somewhere around 17. Whereas this is somewhere around, this is an amine, and this is somewhere around 35. And so being able to know those off the top of your head is really, really important. It makes this process quicker, I should say. However, if you went through the trends, you could say that the more electronegative atom is more acidic. And so the electronegativity of oxygen is 3.4. The electronegativity of nitrogen is 3. So basically what it is that you can either learn the trends and be really good at the trends, but it's probably worth more your time to go with that list of functional groups that I gave you. Because from here, what I can say is, okay, I know that this is an alcohol, so this should be 17. And this is an alcohol, so this should be 17. But I have a fluorine and the fluorine, so maybe this is reduced somewhere down to like 15. And maybe because this one is closer, maybe it's somewhere like 13. And so this is the kind of like mental game that you have to play with yourself, is that you should know what the base standard functional group pKa should be, and then how to modify it based on how we're changing parts of the molecule. And so, you know, maybe if there was another fluorine here, I didn't draw this exactly the same. Let's say maybe there was another fluorine here. Maybe this is 17. Maybe now it's going to like 12 or maybe 11 or something like that. And it's not so important to, the thing that students get really hung up about it as well, and that everybody should, I find a lot of people do this actually, is that they always are like, well, what do I know what the number is? It doesn't really matter. All that really matters is that we are making sure that 13 is lower than 15 and that 15 is lower than 17. And so basically what we're showing here is that there's some sort of like how the inductive effect change that we're trying to get to. And then so we know, and then once again that like 11 is lower than this, and then we can rank these things that are similar, and then we know that 35 is greater. So like this gives us like how to do this ranking. And then finally, like this is much, much different than an alcohol. This is a carboxylic acid, which has a pKa of 4. So it's like, you could say, oh, I know that this alcohol has a carbonyl, quote unquote, alcohol with a carbonyl, and that's why it's 4, but it ends up being like, it's easier for everyone if you just end up memorizing them. They'll come back to haunt you for test 2, test 3. So, you know, if you're able to kind of get these down now, it's a little bit easier. I don't think either teacher gives you a list, which really sucks because, you know, then again, telling people to memorize more things is not fun, but I'll give it to you because I'm the tutor and I can do what I want. So that'll be good. Cool. Any other questions, anything like that? Any topics you want to go over? Anything you want me to foreshadow for next week?
Can you go over isomers?
Sure. So are things like enantiomers, diastereomers, all that sort of stuff on your exam? Or is it just things like constitutional isomer?
Oh,
Maybe, or if you could read me off what the thing is, because I think I'm, oh, actually, I think I have the syllabus. Someone sent it to me. There it is.
I believe we only have constitutional or structural.
Okay. I was going to say, that's good because so constitutional and identical, maybe? Let's see. Oh, the arrangements of atoms in space. Ah, okay. I see. Do you want to, does he have the class notes or Shia? Does she have her class? Or Victor, are you Shia or Poulos?
Shia.
Okay. Does she have like can you take a Snapchat and send it to me of like the section
Syllabus?
not the syllabus, but of like the notes, the like page that you want me to look at. Because I
Okay.
just want to make sure that I do the right thing. In the meantime, I'll draw a tree. Any other topics, anything like that people want me to go over as well?
Victor, do you mean the isomers of like heptane, hexane, or like heptanes, those ones?
Yeah, pretty much like that. Like for an example, she told us to do like all the isomers of octane, for an example.
Gotcha.
Oh, so like isooctane.
Yeah.
Okay.
And then being like able to like say like the nomenclatures for each one.
Okay. This is Debbie. Debbie has, what's wrong with Debbie? Debbie has herpes because she's a hussy. Anyways, write that down. Okay. Yeah. Okay. Sure. She wants you to memorize all of them or just be able to like say what they are?
Just be able to like find them.
Okay. Does
So
she
we
does she want you to know the common or the Iupac naming? Like, because
I think it's the Iupac.
Okay, because if I say the words like isoamyl or amyl octane, or does any of those words sound familiar? Okay, sweet. Oh, okay, makes things much easier. Because teaching the common name ones are not fun. All right, so let's take a look at naming an Iupac. As I remember this lesson plan. So when you guys get into test 2 and you start learning a lot of the functional groups, because right now you're basically naming simple carbon structures, do you need to know how to name alcohols or amines or anything like that yet? Not yet. Just carbons. Yeah. Okay. There are basically 2 points. So for me, for naming, we have 5 sections, but for right now, we only need to know 2. And what I want to show you is, let's say we have a name like this. This name is made up of 3 parts. We have the substituents. We have the parent chain. And we have the ending. Or the suffix, I guess you should say. Parent chain and the suffix. So let's say, for instance, you know what? I'm going to go even beyond octane. I'm going to give you guys this structure. And I say to you, all right, name this. And then we'll go through a couple of octane ones, but I want to give you a fun one. So my steps for doing naming in Iupac, and this same naming will be, the same system will be the same as we get to more and more complex naming, is first step is to identify the parent chain. Find the highest priority group. And then identify the substituents. What I will tell you right now is that this second step of finding the highest priority group is not needed for where you are in the course right now. But it will be super, super, super important for later on in the course because this will be a major step. So better to just start knowing that there is another step that you'll have to know. And so for finding the parent chain, it's honestly just a whole bunch of work of just figuring it out. So if I go this way, I could say it's 1, 2, 3, 4, 5, 6, 7. Or I could do something like 1, 2, 3, 4, 5, 6, 7. Okay, so 7, maybe 1, 2, 3, 4, 5, 6. Well, if I went that way, it would still be 6. So which route do we want to pick? Do we want to pick pink, orange, or blue? What are we in the mood for?
Pink.
I would choose pink. Can we choose orange? Totally. It's also the longest chain as well. All right? There's no reason why, at least in this stage in the game, why we should choose pink over orange. At least for this structure. If, for example, there was like a, I don't know, like a dimethyl group here or something like that, we'd want to choose pink because then we can describe more structures. But at least for the way that we drew it, either one of these is fine. Does that make sense? Cool. So once again, if we had more groups over here, we'd want to choose pink because pink is more descriptive than orange would be. Sweet. Let me erase some of these numbers. All right. And so what I want to do is we've identified the parent chain. So we know it's 7 carbons long. And so we know that, how do we say 7 in Greek? Hept. And then what's our suffix going to be? It's going to be ANE. So we know that this is going to be a heptane. And then from here, we're going to do some shopping. And we're going to figure out what our substituents are. So I see that I have this thing on carbon 5, and I see that I have this thing on carbon 4. And so what I can say is carbon 4 I have a group, and carbon 5 I have a group. And so what's the carbon 5 group called? Who can tell me? 2 carbon chain.
Ethyl.
It's going to be an ethyl group. Very nice. And how about this 4 carbon chain? Who wants to be a master chemist and tell me?
Isopropyl.
Isopropyl. Very nice. So now that I've done my shopping, I can figure out, okay, which order am I going to put them in? So when I put them in order, I always make sure I go alphabetical. So this is going to be 5-ethyl, 5-ethyl, 4-isopropyl. Oh. Does this make sense? Except
Could you go from right to left to make it like the third one for the methyl group?
Exactly.
Or the ethyl group?
You beat me to it. So this is a really common thing that I was going to say, oh, are we good? And then I was going to make a joke, and you robbed me of my joke. How dare you? This is a really, really big trap that people fall into, is that they figure out the longest chain and then they just go with it. But what's important to know is that you have to number both ways for the longest chain to determine that things are going on lower numbers or lowest locants. And so if we look at the purple naming scheme, then we have 4 and 5. But if we look at the red naming scheme, we notice we have 3 and 4. So we want to choose the numbers that are lower. And so what this should really be is 4 isopropyl, 3 ethyl. Does this make sense? Cool. And this naming is the same for whether we're talking about octane derivatives or if we're talking about literally anything else. So if we want to take a look at an octane, then, oh, I don't know. Like, can you guys hear that? I think that's a turkey. That's so weird. Honestly, I feel like I live in the middle of nowhere. Although the turkeys near my apartment are assholes, because when you're trying to drive up, they do not move. It's like they want to become Thanksgiving. And I won't mind if I hit them. So, but all right. So you're given something like this, and you're asked to name it. And so first steps first is to identify the parent chain. So I don't know. Let's try numbering this way. 1, 2, 3, 4. This would be 1, 2, 3. So that's too small. I have 1, 2, 3, 4. So what do we think? Which one are we going to choose? Green or yellow? Does it matter? No, it doesn't matter. We end up having the same thing. If we choose the fourth way, or the green way, then we have 2 methyl groups. And if we choose the yellow way, then we have 2 methyl groups. So they're exactly the same. So it does not matter. And so I'm going to choose the yellow way because I have the stylus, so I can do what I want. And so I have 4 carbon chain, and to say 4 carbons, we say, not tetra, we say methylpropute. And our ending is going to be A and E. And so now we do some shopping. And so we say we have a methyl group on carbon 2. We have another methyl group on carbon 2. We have another methyl group on carbon 3. And we have another methyl group on carbon 3. So whenever you have groups that are the same, we can group these all together and we can say we have tetramethyl. So our answer here is going to be tetramethyl. But because we're using a multiplier, tetra, meaning 4, we have to use 4 numbers to describe where those are. And so this is the thing that I see people kind of missing a lot of the times, is that this is a multiplier, so I better see 4 numbers over here. Same thing, if I see di, I better see 2 numbers. Tri, 3 numbers. Penta, 5 numbers. If I don't see that, you've done it wrong and shame on you. All right. The other thing that I see people doing all the time is they're trying to do this. 2,2-dimethyl, 3,3-dimethyl. This is not a thing. This is wrong. All right. If it is the same functional group, if they're all methyl groups, they all get smashed together. No matter if they're on carbons 4, 8, 15, and 25, we don't care. If they're the same functional group, they all get put together. Does that make sense?
Why isn't it like 2,3-dimethylbutane?
2,3-dimethyl. Good question. So his question is saying, why isn't it 2,3-dimethyl butane? The reason is because this multiplier is saying that we have 2 methyl groups, right? And even though I'm writing 2 locants here, how many methyl groups do we have in total? We have 4. Does that make sense? Cool. Very good question. So remember that the multiplier is on the die and it describes how many groups in total we have, and that we have to smash them all together and add them to a total. How do we feel about another practice one? Should we do another one? Yep. No, we're good. Okay. The big thing about naming is that it's the more clever you try to be with these problems, the more you get it wrong. Simple is best. So if you think it should be more complicated than what it is, you're probably doing it wrong, especially at this stage in the game. So trust yourself, do some practice. There's a fantastic website. No. Here it is. This org chem 101, they're just typing practice naming organic compounds. This is brilliant. So you guys are going to be doing naming and drawing probably. And your only functional groups are here. So I don't think you guys are doing functional groups yet, right? Oxygens, chlorines, fluorines, that stuff, not yet? No? Okay. So, and then from there, you can also customize further. When you guys start learning more, you can start putting it in. And what it does is that it generates either the name and you have to put it in, or it generates the structure and you have to name it. So it's really good. There is another website that I use a lot. It's called Opsin. And basically what it is that when you enter in a compound, and if you did it right, why isn't this working? There it is. If you do it right, it will spit out the correct structure for you. So either you can do Opsin or you can do that organic naming organic compounds. Honestly, I think this one is better. OrgChem 101 is what it's called. Great, great, great website. A lot of help. Likewise, if you go, I thought I had one. Oh, I thought I had a thing. Maybe I don't. What I will say is that if you guys ever want to go more in depth into a topic, but you don't want to read the textbook, you want to see how another professor goes about it, go into the BU Orgo folder. You guys are in the first semester. Go to the class notes, and this will have a lot of topics in here that are explained another way, but not like a textbook. So Dr. Rubio would go through and he would like talk about all this stuff, and it was brilliant. So if you're ever like, oh, I kind of sort of understood what Gabe was talking about, but I wish I could have another way of doing it, here it is. He's brilliant, great, great guy. Here's this whole thing about nomenclature as well. So it's fantastic. Any other questions, anything like that that I can answer before we go away?
Will your sessions be like weekly, or did you not figure it out yet?
So Orgo for MCP is Monday, Wednesday, Thursday, Friday. Monday, Wednesday, Thursday, Friday, 4 to 6 p.m. And then you guys, your exam is on Friday, right? So this Thursday, it will be, instead of the regular 4 to 6, it'll be 8 to midnight. So I always do a midnight review the night before exams. So it's kind of like the final time. Come, sit in, listen. I'll just go through tons and tons of problems. Last year, I would buy everybody hot chocolate. Like I get the Dunkin's hot chocolate. We just make like a big night of it. So I'll go through. It's less for this exam because there's only been a couple of sessions so far, but more so for exam 2 and 3. People really like this because I'll go through lesson plans that people are still having trouble with. I'll go through entire practice exams. I'll talk about specific things. So the more stuff that you guys send me over the week, the more stuff I have to prepare for the midnight review. So whatever problems you're stuck on, whatever you're like, oh, I don't really get it. Even if it's things like, oh, I think other people would benefit by having this, let me know. I'll figure out what we can do for the midnight review. And that way you guys can go to bed at midnight and not stay up all night doing random shit, like trying to memorize Pka values. It's treated though. Cool. You know what my bio teacher in high school did? She drew a tree like this. She didn't draw Debbie though. And she drew this. And we're like, what are you doing? She's like, oh, I'm drawing a corn tree. We're like, what do you mean a corn tree? Because she was from India, so we thought, oh, maybe she just didn't. And she wrote on the board, she's like, this is a corn tree. It's like, how the hell are you a bio professor and you don't know that that's not even what, it's not what they look like. Like, God. Oh Miss Gupte, what are we gonna do with you? Oh, this is what maybe I can put some like grass. Perfect. Perfect. Cool. All right. I will see you guys on Monday. Let me know if you have questions. If someone wants to let me know what you guys are going over next week, just send me either like the syllabus or if she puts out a schedule or anything like that. Also know that generally, so for the first semester, Poulos and Shia are pretty similar in topics. I know Poulos's class a little bit better, and generally Poulos kids do worse and need my help more. So for those of you in Poulos, have fun. It's just what it is. It's a trend that I find, but I don't have a ton of. I have it somewhere, but if people in Shia's class want to send me like what you guys are going on, I can take a look and talk about things. Cool. Sweet. All right. Have a good weekend. I'll post on my Snapchat when this recording goes up, wherever it goes, and then we'll be golden. It'll be, oh my God, so much fun. Cool.
Thank
Thanks, Gabe.
you. Yeah,
welcome.
thank you.
Bye.
Thank you.
Thank you.
Thank you, Gabe.